All right, everybody. I hope you can hear me uh, well enough. And I'm just going to do a relatively, I'd say, brief overview of the material that we would have been doing today, which was Wednesday the 20th. But due to the room change and the logistics involved with it, and the fact that we have limited folks available today, we're going to do it this way. So without further ado, I'm taking you here. And this is kind of where we left off, so about antibodies. Immunoglobulins, the globulin portion, about 36% of the blood, are both mostly betas, which are carrier molecules, and gamma globulins. And the whole idea, I mean, it's a B cell activated thing, and we have the five categories. The acronym to use is called MADGE, MADGE, for the major ones. We'll take a look at that, and that's good because they're IG, which is short for immunoglobulin, M, A, D, G, and E. And G is by far and away the most abundant. We'll talk about that in a second. So, I mean, whether you think it's a T or a Y, but we should remember from biochemistry, heavy chains and light chains with the hinged area in the middle, and the variable, and you have a constant region at sort of the base of the T or the Y, but at the wings, you have a variable region, and that's what is fashioned uh, from a standpoint of the protein or the polypeptide chains that is designed specifically to attach to the antigenic portion of, let's say, the invader, the virus, the bacteria, the altered cell, etc. So as you can see, and again, they call this the effector because it really determines the classification of the antibody and the kind of cells, the things that it does effectively. And I mean, and there's a variation. Complement, which is activated as part of the inflammatory cycle, may play a role. That's where some of those opsonins came from. Some are in the bloodstream, some are in the secretions, and so and that maybe is a very interesting little nuance. Understand that we don't just make antibodies or just get them from our mom and they disappear in 6 months. We make antibodies genetically. We are pre-programmed to make a lot of these antibodies over the development over how many generations of us and where we live, and it differs from geographical to region and ethnicity to other areas. Not dramatically, but enough that it's significant. That's there. And here's the classic example of the heavy and the light chains. You can see the bonding that's there without going into the chemistry of it and the spatial kind of a diagram. So they're not small, but I mean, molecularly speaking, they're not small, but they're small in the context of the unbelievable amounts of them that are produced. Here are the classifications. The IgM is by far and away the largest, and it's the first one produced. So, from a medical perspective, when we fractionate proteins and do antibody fractionation or measure for certain ones, and effectively titrate or assay, the IgM, if we see an abundance of IgM of a particular type, we know we're in the earlier, the acute stages of an infection. Where if you see an abundance of IgG, most likely you're in a later stage or it's a secondary challenge that has occurred, where your body ramps up and produces IgGs a whole lot faster. By and large, as a pentamer, and you'll see it structurally, it agglutinates very, very rapidly. In other words, it latches onto multiple of these items, and what agglutination is, it basically takes them from being either dissolved or difficult to identify into a large clump, which is more easily identifiable and attachable to a white blood cell. So it's about fixing and activating complement. The IgAs are in all of our secretions effectively. It may start as a monomer, but mostly we find it as a dimer. Okay, so you'll see the illustration of what they look like, and it's really a sentinel. It's probably more about our innate system than anything else. And again, part of that pre-programmed stuff that I was talking about, depending on wherever it's located. It's really important to understand. That's the kind of thing that that we can certain things can eliminate, so to speak. Uh, we need them to be there. Like folks, when I think of it as this navage, this nasal flushing system, okay, you're clearing out the particles and all of that stuff. You're clearing out the IgA too. I mean, there's a fine line between not enough and too much. People don't necessarily understand that. Here's the IgM. Here's the IgA. So you can see if this latches on to 10 different particles, it's going to be a lot easier to tag. And effectively, that's what your immune system does. It tags it, slows it down, deactivates it, and basically macrophages come up and are waste removal surfaces. Here's the IgA. You can see where it is. IgD is probably a facilitator that becomes part of a B cell receptor. It's not as clearly understood. Maybe you covered it to some extent. I'm sure if we were doing immunology in the Dr. Maurer sense, you might get more of it than I'm giving it to you. The IgG is the vast majority in the plasma. Secondary and late primary responses. Yes, it crosses the placental barrier. Yes, that's the protection you get from your mom when you're born for the first 6 months or so. IgE is interesting. It's really the one that attaches to basophils and mast cells and plays a pivotal role in allergies and particularly anaphylactic shock in a more dangerous sense. And that parasitic aspect, we talk about parasitic infection. Parasite is a specific term here referring to eukaryotic pathogens, worms, certain kinds of fungi. These are things that basically that Ig triggers the release of particles that begin to assault these larger pathogens as opposed to bacteria and viruses, which are much smaller, and begin to break them down and make them easier to dispose of. The term parasite generically means something that occupies you and it thrives while you're to some extent harmed. So that could be anything, but here the context is eukaryotic. Context is important in MCATs. Are we talking about what a parasite is generically, or are we talking about parasitic infections in a medical sense? That's different. And again, some more pictures and stuff like that. So B cells can switch, okay, even though they have specificity for the same antigen. So IgM early, IgG later. Secondaries are IgG. You can switch to other things depending. Again, this is somewhat, to me, that's a little bit about the pre-programming that goes in there. So the big misunderstanding is that they're somehow destroying the bacteria, the virus, the whatever. They don't. There's 4 different ways they deactivate. When toxins, which bacteria produce in abundance, they neutralize them. For certain items, they agglutinate them, meaning they form those big clumps. For ones that are very, very dissolved, they precipitate. And other ones will fix complement to facilitate any one of these events or other things that are there. So there's quite a lot that goes on. As I said to you before, you won't have to know all of this material for the immune system, but you should be at least tacitly familiar with the way we phrase it, some of the nomenclature, some of the generalities of how things work. So it might, answering a question might boil down, well, about antibodies, and you might find the wrong answer by saying it destroys the blank. Well, immediately you can eliminate that answer, or if it's one of those, all these are correct except which, boom, now you got your answer. See, that's what you got to look for. Wording is so critical. Read the question. I have said that a million times, and I'm sure I'll say it a million more annually. Neutralization, effective, lots of toxins, okay, or blocking sites where toxins attach to, and then we have phagocyte. Agglutination, basically these lattice-like clumps. Classic is the blood cells. We remember the little speckles we saw when we were doing the blood testing. Precipitation makes them soluble, makes them complex, come out of solution. Again, easier identification. And against cellular antigens, ones that are on the cells or within the cells, and of course the mismatched RBCs, okay, complement binding sites on their stem seed regions align. So when they align, they trigger complement, which will help to lyse the cell that's been involved, amplifying the inflammatory response. Opsonization, like I said, they attach there to facilitate phagocyte. There's a lot of stuff that goes on. Very interesting. You have a good chart with that. So the worms, this is that lysis by complement, Ig antibodies. This is the idea. They bind to the surface of worm, making it destruction for eosinophils. Eosinophils then release these toxic contents and begin to destroy it from the outside. So that's really specific to worms. That's probably the parasitic infection they're referring to. I don't need to worry about plan or anything like this. You heard me talk about it a little bit before. Tumor cells and B cells. This is how they generated the monoclonal antibodies. And they're not new on the spectrum. They weren't just here because COVID magically appeared. This is how they developed as effective as any treatment for people with COVID, whether they were vaccinated or not vaccinated. And yes, we can do the same thing with regard to we can clone antibodies that work in regard to infectious approaches to cancer treatment, which I'm not here to tell you about because I'm not as familiar with it. But they're nothing new on the horizon, and they're a very useful tool. They're very expensive to make. If you didn't know, or if I didn't tell you, I mean, my kid got a bill for $2,000 for the monoclonal treatment. I mean, I don't know how much it cost. Maybe it was a few $100s, and they just jack up the bill. It was covered because he tested COVID positive by the government. But it's funny, his health insurance didn't cover it, but his COVID. But during that particular time, it was covered when we were in the throes of COVID. Okay, and all this stuff is a summary done. Okay, so that's the first one. I'm going to try to get through as much of the uh, T cell related and the B cell activated relating material as possible. So let me scroll over to that and get this guy started. So this is more about the adaptive, and down the road it goes into allergies and reactions to transfusion, different kinds of things that we talk about more in lecture. The big thing about T cells, B cells is floating, is things that are not inside of the cell. So when it's intracellular, everything changes. And there's a good animation in here that you can watch. I'm trying to find where I put my coffee. I'm sitting in the office doing this. Viruses or bacteria, cancerous or abnormal. So abnormal cells, whether transplanted, transfused, cancer cells, which by definition become abnormal cell. Viruses or bacteria that go inside a cell. HIV goes inside of a white blood cell. Unfortunately, it's one of the cells here we're going to be talking about. Bacteria, tuberculosis inside of the cell. Plague inside of the cell. And we can have cells, and we call them, in the old days, killer T cells. Now we just say cytotoxic. It's the more appropriate term, the one you would probably say. But that's what they are. And they kill sometimes directly by, and you'll see some of the methods, and sometimes they use chemicals that play a role in immune regulation. There's a lot of chemicals. That's part of this too. So you're going to see that there's distinctions, and there's a lot. T cells are your best friend and your worst enemy. It's the best way to phrase it. Without them, your immune system fails and you're going to die from infection or other things that are part of it. On the flip side of that, if they're overactivated, you're going to die from that too. So there's a lot of stuff that goes on. We'll deal with more about that, particularly in a classroom perspective. If you haven't had me for the, as most of you have not, for the immune system part of the lecture program in advanced phys. So they're a lot more complex, two different populations based on the receptor. So we call them CD4 and CD8. CD4 cells are the ones that become helper T cells, T sub H. They activate B cells, T cells, macrophages. They are the single most important cell of your immune system, period, end of sentence. Okay. Most of them become regulatory T cells. They are not only to turn on the response, but more importantly, to shut off the response. We used to call them helper and suppressor in the early days of HIV and AIDS, where we really didn't know a lot about it. Now we sort of generically use the term regulatory. Understand your immune system, once it's switched on, if it doesn't get switched off, it's a problem. Antibodies have a lifespan. They only produce for a certain amount of time, and they only exist for a certain amount of time. Whereas these mechanisms, we need to have an off switch, and that's what the helper T cells, in a regulatory sense, are part of. And of course, they're memory cells, and that's an important part about various kinds of immunizations as well. CD8 is the marker. It's a glycoprotein marker like CD4, and they become the so-called killer T, more appropriately T sub C or cytotoxic C cells. And they either can be basically the active cell, which is the cytotoxic cell, or a memory version of it. So they can be an effector or a memory cell. So helper, cytotoxic, and regulatory are all the forms of activated. So when they're non-activated, we call them CD4s and CD8. Once they're activated, now we have different names for them. As you can see, naive meaning unactivated. Doesn't mean they're incompetent. Naive means they haven't been really put on the path of usages yet. And this is the whole idea. So you have different, if it's a CD4 or CD8, you're going to have some kind of antigen presenting to it. So once that antigen presenting cell, some kind of dendritic cell or a modified macrophage, if it presents it to a class 2 marker, okay, most of them will be effector or helper T cells or regulatory T cells. Some will be memory cells for future usage. Okay. On the other hand, if it's a class 1, it will activate the CD8 cell lines, yes, memory cells, but now we're going to get these cytotoxic T cells. And you're going to see down the road, they work in concert. They're not going to ask you about the intricacies, I would think, so much. But it's going to be important to understand. It's a gift. If you have the capability of looking at a chart or an image and are able to recall it, if you can just try to work on that to increase sort of the photographic aspect for images, diagrams, illustrations, it's amazingly helpful. I'm lucky I got that. I mean, there's lots of ways to improve it, and I'm sure there's lots of videos and YouTube things that can help you with that. So it's only these little fragments of these MHC proteins and relying on antigen presenting cells, and class 1s are all cells, and RBCs don't count, don't have a nucleus, they're really just matured and adapted for oxygen. We talked about class 2, AB displayed by APCs, dendritic cells, macrophages, and B cells. Okay. Class 1. Okay, and they go into what it binds to, whether it's self, whether it's now. So class 1 MHC is the critical. Remember, class 1's for CD8, class 2 for CD4. Class 2, different size fragments, CD4 and helper T cells. And effectively what they're doing is they're basically, and that's the whole idea of the helper T cell. When it is contacted, basically it immediately starts to secrete chemicals that indicate that the innate immune system is being activated. It goes back to that original sort of construct. We have a hard boundary, then a physical boundary, then we have more of a cellular boundary. And now if we get past those boundaries, if we get past the wire fence, if we get past the guards and on patrol, and we get into the building itself, once the alarm goes off, that's the helper T cell, and it goes double the guard, check all the boundaries, call up the troops, send out signals, open the armory, whatever, however I do it in a military sense, it's happening for that type of stuff. Okay, because that's just sort of my way of thinking about it. Make it any way it works for you. And they give you all of this. So whether it's, and again, foreign antigens or MHC or endogenous intracellular pathogen proteins, cancer cells, exogenous bacteria. So here they're looking, I don't know why they put a viral, other than to think that the virus is in there, and you can look through that if you want. Okay. And I'm not going to get into the restrictions and blah, 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 blah. We'll cover more of that. So T cells are a co-stimulating process. And again, the interesting nuance, that's something that you should be familiar with when you come to taking MCATs, is that one of the significant problems is that the cell that's affected by HIV, and it hijacks this co-stimulation antigen binding mechanism on the CD4 cells. It attacks and destroys and takes over and poisons the lineup, any way you want to express it, of helper T cells. Years ago, we looked at the ratio of helper to suppressor, but since the terminology changes, we're able to measure in the bloodstream specifically the number of helper T cells. Once it falls below whatever a critical level, that's 200 per whatever unit. Okay, at that point, your immune system's done. They're no longer functional, and you're going to succumb. That's an AIDS-defining diagnosis. Okay, and you'll see a little bit of this. There's different kinds of receptors and this double recognition. So those are just things to remember without going into all the ins and outs. So it has to bind to co-stimulus signals on the surface of the APC. Without it, it doesn't work. So you have basically has to, the animation will show you, okay? And let me see if I can get to that so you can see it before we go through here. And you should be able to play this fairly well before I go back to that. There's a lot of stuff here. And maybe I'm glad we're doing it this way and all the different things that it is, perforins and granzymes, what it looks like, killer T cells binding to it. You can see it, cancer cells are just impossible to look at. You can't play the media? I have no idea whether that's being disabled or not. Okay. Really? All right. I'll make sure we come back and do it. Let me flip back, and I'll try to find a way to send this to you if I can. That's crazy. I said I'm on my office computer. Okay, let's do it this way. Well, I'll find a place where we can listen to it and I can play it somehow. It's not a big deal. And I can send it to you separately, and I will. Might play better when I'm at home. So let's see if I can give you an idea. So here's a bacteria. Okay, bacteria is genetic. It's going to end up with a B cell response. Okay, most likely. And now you can see here we have this. It's a two-factor. You have the co-stimulatory on the dendritic cell. You have the co-stimulatory and being presented on the class 2 MHC. They both have to bind, and then that will activate the system. And now you have these helper T cells activated. What does that do? Helper T cells either themselves or induce others to produce what are called interleukins, IL for short. Okay. They basically are the chemical messengers, and collectively they're all cytokines, and cytokines are extraordinarily powerful. They're summoning cells, they're dilating blood vessels, they're diverting circulation, they're outpouring white cells, they're activating other cells. So you can get a storm, we call a cytokine storm, in very severe diseases like toxic shock syndrome or scarlet fever. Okay, so you're going to see IL-1 typically is released more by CD8 cells, and IL-1, and also macrophages, you can see here, will stimulate other T cells to release the most important one, IL-2. We've known about IL-2 for a long time. We can make it genetically. It was a first-line cancer treatment for years, but very, very harsh, very, very powerful. And it'll make more receptors for it as well. So this is the key growth factor. So, and why it was used in cancer treatment, it would act on cells and to release more of it and other T cells. So T cells, we got busy. And the way we fight cancer endogenously is that, I understand there's a whole thing about cancer treatment by and large. For years it's been removed. And nothing wrong with this. This is what we had available. Removing it and radiate the heck out of it and use poison chemicals we call cancer chemotherapy. In the hospital we call it passing poisons. I don't know what they say today, but that's what we used to do. You're basically trying to kill the tumor before you kill the person. There's no other way to say it. And so there's a lot of different responses. There's other kinds of interferons other than the typical interferon we hear about so much with viruses. And interferons have been used to deal with viral infections. So there's lots that goes on with this. It's a useful chart that you don't have to know for now, but again, so Alpha and beta interferons, those are the ones that you hear about. That's part of our innate defense. And then the natural killer cells will be on patrol for those viruses. Gamma, okay, much more involved in a more adaptive system. IL-1, activated macrophage, I may have misspoke. It basically encourages the T cells to do other things and pyrage it. IH2, IL-2 rather, helper T cells, stimulates all lines, regulatory cells, everything. The whole idea is now we have an invader that's breached our defensive. We have to get everything busy. And then all these other things that are there. Ones that are inhibitory are noteworthy. So IL-10, secreted by macrophages, helper T and regulatory cell, inhibits macrophage, other genes, turns down the innate immune response. So that's something, not all of these are what we call pro-inflammatory. This is a bit more anti-inflammatory. Most of the rest of these, IL-17, very important in both. So, and plays a pivotal role in autoimmune diseases. For the longest time, several years, I was on Cosentyx, which she advertised. Cosentyx is an IL-17 blocker. So IL-17 is pro-inflammatory. I'm taking it as anti-inflammatory, which I found it increasingly harder to tolerate. I felt I had more side effects when I took that shot every other week. It was like, ugh, or every month. I don't remember how often it was. I felt lousy. Now, now I use one that's in this category called tumor necrosis factors, and they're advertised all over. Mine is this is Humira. Phil Mickelson's been advertising for years because he had psoriatic arthritis, like my first rifle does, and I have a variation of Enbrel, which was an early treatment. I think the Humira is more popular and very easy to administer. I didn't like that either. Okay, I felt funky for days. So, and here you can see there's other factors that are anti, and there's different suppressor factors. So TGF, tumor transforming growth factor beta, and IL-10 are ones that you might want to encourage in influence. So you look for these. Again, remember exceptions. Most of these are potent pro-inflammatory with this exception that are there. So I've stopped taking that now, and I'm hoping it responds. So it's all about this. Once primed, these helper T cells activate the lines, proliferation, cytokines. Without them, you're toast. Okay, and there are a variety of ways that they do it. We're not going to go into it. I'd rather show you the thing. Again, this is very complex. So, helper T cells are part of the process that work in concert with a cytotoxic T cell to activate it along with the antigen presenting cell. There's a very complex interaction that animation does a good job with. So I think that's part of it. And they summarize a lot of these that are there. And then they'll go into the ways that these destroy. So I'll probably conclude with this in the interest of time. So unlike chemicals that are tagging and let macrophages kind of clean up the debris, okay, tagging, damaging, altering, this is a direct attack. So they're there, they attach to the displayed markers. Again, cancer cells can change them. Virus, intracellular parasites, bacteria, cancer, foreign, the lethal hit. What they do is they release perforins, which are like tiny protein poke holes in something, like perforated, and they shoot granzymes in it. So these are enzymes that will literally stimulate apoptosis. Amazing. Say pop these little perforins, and in come the granzymes. Here's the target. In come the granzymes. They go through those little openings, and voila, they're done. Okay. And again, natural killer cells are also part of that. They're more part of our innate system. Okay. So they don't have that. Maybe they have antibodies. There's different things. So they're more of surveillance. And again, whenever you see a slide and you see lymphocytes, like we looked at in the lab, they're going to be one of these two that are there. The regulatory ones have to suppress it. Okay. They secrete these different factors because if this doesn't get turned off, it's awful. And that's probably one of the reasons we worry about them with autoimmune reactions and trying to reduce rejection of transplant. There's a lot of research done in that. So in that regard, we'll stop it there. That's what I have to cover because the grafting to me is, I mean, I'll chat about it, maybe just to conclude this, but we'll do that another time. Well, hopefully on Friday, depending on the room situation, we will look at. I'm trying to think of the best way to express it. We'll look at some passages. I'll see if Dr. Hillig has another passage for us, etc. So thanks very much. I'm going to conclude this as we speak now.